Awesome. Well, it's great to be here. Thank you for having me. My name's Evan Haas. I'm co-founder and CEO of Helix Carbon, and I co-founded this company actually out of MIT, like everyone else here, and along with my co-founders Ariel First, who's a professor in chemical engineering, and Dave Brown, who was a graduate student with me. I was a graduate student in mechanical engineering and also in business. And we spun this out a lot of the work we were doing in sort of around materials decarbonization, and specifically, how do you use electrochemistry to produce materials with no carbon impact? And within that, we're focusing first on the iron and steel industry. And this is one that obviously has a huge presence here in Japan, but it also has a presence globally in terms of emissions. It's roughly 7 to 10% of global greenhouse gas emissions. It's a $2 trillion industry. And the vast majority of those emissions come from the very first step, primary iron making, turning iron ore into metallic iron. And if you look at the way this process works today, those emissions come from the fossil fuels that we use as a feedstock. So those fossil fuels, usually natural gas or coal, are fed into a reformer. Those compounds are converted into carbon monoxide and hydrogen, which each can strip an oxygen off your iron oxide, your iron ore, and is emitted as CO2 and water. And it is really this CO2 that is the source of those 2 gigatons of emissions globally. And the challenge with decarbonizing this is these plants, these furnaces, there's about $1 trillion of them deployed globally. And many of them have decades of operating life left. So how do you decarbonize an industry without decarbonizing the facilities that you already have? You have to develop a technology that is compatible with the process that you're using. And so our answer was, instead of letting this CO2 get emitted, let's actually close this cycle. Let's take the CO2 and water vapor that's being emitted, pull it into our proprietary electrochemical cell, and co-electrolyze the CO2 back into carbon monoxide and the water vapor back into hydrogen. Now, the key here is this feedstock is chemically identical to what you're already getting from fossil fuels. And so it's a drop-in solution, a drop-in chemical at existing iron-making facilities. And at the end of the day, you get the same identical sponge iron product. So in order to do this, we had to solve 3 core technical challenges, which were really sort of formed the base of our business. The first was electrochemical stability. So there's a lot of CO2 conversion electrolyzers out there. The core challenge that many of them share is stability. Many of them will fail after 20 or 30 hours. And we've been able to demonstrate hundreds of hours of continuously stable production, and that's really key to some kind of commercial deployment. The second is, if you want to do this sort of cycle that I just showed you in an economic way, you have to be tolerant to everything else that's in this stream here. And that includes excess carbon monoxide, hydrogen, methane, nitrogen. There's so many other compounds in there that in many cases are toxic to today's CO2 conversion systems. And so we had to develop a system that is able to be resilient to all of those and operate in low concentrations of CO2. And then the last one, which is ironically the easiest, is just having a very tight control over the ratio of hydrogen and carbon monoxide that you're producing, being able to very reliably keep consistent with that, because that's what those furnaces are sensitive to, is the ratio of carbon monoxide and hydrogen. And so that's the cell that we built. It's a gaseous phase carbon dioxide conversion system that pulls in flue gas, whether it's from an iron plant or any other industrial facility, and can co-electrolyze the components of that flue gas into the chemicals that those facilities already use. And so in the context of iron, obviously that's carbon monoxide and hydrogen. And we also make a lot of oxygen, as you might guess, at the anode, and that's also something that has a ton of value at an industrial facility. And so we've already talked a little bit about stability, and also the core piece of that is not just stability of output, of how much you're producing, but also stability, again, in that ratio of hydrogen to carbon monoxide. And so we've shown that we can actually produce a gas blend that is exactly what you would get from natural gas or even coal, but with this electrochemical closed-loop process. And so, as you might guess, that we're starting in iron, but this is not a technology that is limited to just this industry. The ability to produce carbon monoxide is a ubiquitous chemical feedstock and has a lot of applications in things like chemicals production for polymers, polycarbonates, polyurethanes, acetic acid, as well as a variety of metals like copper, for example, that also go through a similar kind of reduction process. We've also developed a catalyst that uses the exact same cell. It's a copper-based catalyst for conversion of CO2 to ethylene, which we heard a little bit about earlier. And that cell is fundamentally the exact same system that allows us to take dilute CO2 and produce that chemical feedstock. And so the reason we're here in Japan is because Japan is a leader in these spaces. We've already spoken to many of you, but both in steel and chemicals, many of the leading companies are based here, and we're excited to partner with you. So for us, where we are right now is looking for some of those first deployments. We have a couple pilots we're developing in the United States, but we're looking to expand, particularly with pilots in sort of this 1 ton per day range, as well as joint development agreements. And if you're a buyer of green steel, we'd love to talk with you about how we can support that. So with that, thank you for having me, and hopefully come by and chat with us later.